Good afternoon, everyone. Thank you for this opportunity to speak to you. So today I'm going to talk about materials chemistry and us and innovation, right? So materials chemistry has been the force that has taken civilizations ahead. For instance, the industrial revolutions, the first one was based on coal, then came gas, then more recently in around 1970, the industrial revolution was based on electronics, and now the last one, the fourth one, is based on internet and renewable energy. So materials have taken us forward. But the thing is that in this journey, many a times this entire development has not been thought through, right? So in the first two industrial revolutions, it took the society forward in terms of manufacturing, in terms of transport, but we did not really think about these molecules. When they land up in the environment, they would cause the air and water pollution. They would land up in the food we eat, in the water we drink, in the air we breathe, right? So my point is that we have to think this entire life cycle through as to when we design these molecules, when we take them forward, when we adopt them, can we design for sustainability, right? Can we think of the entire life cycle of the material, of the molecule? What would be its lifetime in terms of emissions, in terms of end of life, in terms of the replacement burden? So that's exactly as a civilization how we have to think of when we innovate and when we create new materials, when we bring new technology forward, not just now and today, but tomorrow and in the future, right? So this is basically the topic that I chose today to bring forward as to materials chemistry for a cleaner world. So this is just a picture of what I was just talking about, where a lot of the manufacturing processes, the toxic gases and emissions, they land up in the environment, right? And this creates a very difficult scenario. In 2019 alone, in India itself, there were about 2.3 million premature deaths due to air pollution, and around equal number due to water pollution. So how come these molecules are landing up in the environment? Can we design the technologies where we sequester, where we pick out and absorb these molecules to be able to harness them back, to be able to reuse them and recycle them back in the same processes? So that is my simple message. And it just requires a little bit of practical thinking and emphasis on the part of the reuse of these molecules. And because they're causing repercussions on human health, right? So that is the message. For instance, I'll give you an example of carbon dioxide. Now, what does nature do with carbon dioxide, right? In the simple process of, actually it's not simple, but in the process of photosynthesis, what it does, it takes the carbon dioxide molecule, it takes light and water and converts it into food, right? So when we are designing our processes, can we think of how nature did it? Can we design materials and processes where we take out CO2, shine renewable energy, or impart renewable energy, put water in and create useful products? So that's the kind of materials engineering and chemistry that I'm talking about. So this is, through my talk, I just want to encourage this kind of simple practical thinking where the entire life cycle of the molecule is thought of, where molecules can be converted based on biomimicry, on how nature does it, on simple practical thinking, right? And each one of us can have this innovative, have this innovative thought of being able to complete this life cycle. So there's another very big problem that we created. in terms of materials. A material that all of us use in our everyday life. Yes, I'm talking about plastics, right? So plastics have been a great friend, but also a big problem. So they're cheap, they are useful, and they are everywhere. So in 1950, about 2 billion metric tons of plastics were generated in the world. In the year 2050, it's going to be around 500 million meter cube of plastic. So that's a lot of material. And what happens is that the beauty of this material also is that it does not easily degrade, right? That's why it's so sturdy. That's why you can carry things in it. You can hold things in it. It's used a lot in engineering also. But it does not degrade. And that's also the problem. So it stays in the environment, as we know, for hundreds and hundreds and hundreds of years. So although this material is very useful, could we take a page out of the materials chemistry book and make it degradable, right? And as I earlier said, can we do it like nature does it? Can we take sunlight, materials like a catalyst, right? You're familiar with catalysts. They simply accelerate the rate of the reaction. So can we impart these kind of molecules into the plastic so that when there is an end of life, remember the circle we started with, we have to think about the end of life of that material. So when this plastic reaches its end of life, there's sunlight shining on it, there is a catalyst that is built inside that Bisleri bottle that's lying there, right? And when it touches the soil, there's bacteria, there's microbes. So all these act together to either degrade it or create a value-added chemical or fuel out of it. So this is the way we have to think when we are designing for the environment, when we are designing for humanity, actually. So where the materials, we just don't think of the now and the present, but we think of the future. So we all have lived through the pandemic, and that's another area where materials chemistry can play a very big role, and it has to a good extent already. But as young people here, this is another area where materials chemistry can help us to deal with microbial infestation. So we can create some very special surfaces. This is just an example of a super hydrophobic surface. What I mean by that is it repels the water, simply repels the water by creating a hydrophobic or a sort of non-polar surface. Now, this kind of surface, like Teflon or any slippery surfaces, also does not allow bacteria to sit there. So that's an example of how materials chemistry can help to create surfaces that do not allow microbes to proliferate and to grow there. There could be other types of surfaces like shown in the picture here, which is like leachable surfaces, which give out tiny materials which basically kill the bacteria. Or it could be a surface which is very, very rough, where the bacteria, when it comes in touch with it, it basically dies. So this is another example how clever materials chemistry thinking can help us to live in a cleaner and safer world. So everyone, that is the message I wanted to convey today, is that innovation can happen by simple practical thinking, and we have to design materials, design molecules, thinking about the entire life cycle. And it has to be a circular life cycle, right? As I'll go back to the initial circle that we started with, where we have an ideation and design space, where we think of what we are doing. Then there is a product, which all of us use, all of us create and use. But think of the entire life cycle as to what is it going to be its lifetime, where is it going to end up? Can we use it back, or it's going to have a deleterious effect on our health? Think of the end of life, and then what is its replacement burden, right? If that plastic that we used today, that's going to persist for another 500 years, or that insulating gas that was given out in the air, that's going to stay for 50,000 more years. Is it worth it? Are we doing things the right way? So with that, I'll end my talk.